increasing, decreasing, and constant functions. A function f is increasing on an interval when for any x1 and x2 in the interval, x sub 1 is less than x sub 2, implying f of x sub 1 is less than f of x sub 2, right? So those y value, this y value is smaller than the next y value. So that's true if we take a look at this example here. Say, for instance, we say this is x sub 1 and this is x sub 2. Notice that this y value is definitely smaller than the other y value here. That's what it's saying. Another way to look at it is that it's going up from left to right if we can see a graph. A function f is decreasing on an interval when for any x sub 1 and x sub 2 in the interval, when x sub 1 is less than x sub 2, implying that the y value is bigger than that second value. So if you take a look at this example here, this is our x sub 1, and this is our x sub 2, right? This x value is smaller than this x value. That's what this is saying. And if you look at the y values here, notice that the first y value, y sub 1, is larger than the second y value. And a function f is constant on an interval when for any x sub 1 and x sub 2 in the interval, x sub 1 equals x sub 2. So the y values are the same. It doesn't change, like you can see in this example here, right? That doesn't change. It's constant. And then for decreasing, I know I said that for the other one. For increasing, decreasing, it goes down from left to right. So let's describe function behavior. Determine the open interval, so it does say open intervals, on which each function is increasing, decreasing, or constant. So we're not going to put brackets on here. It's just wanting the open intervals. So let's take a look. We want to see where it's increasing. Increasing is when the function is going up. So we can say this is the first place that it's increasing. That is from negative infinity, and the highest x value right there is negative 1. So it's in terms of x. So it's increasing at this point, and it's also increasing, let's see, and between 1 and positive infinity, right? So we're looking at the x values again. Now let's look at decreasing. Where is it decreasing? It's decreasing in the center in this example, from here to here. Again, we're looking at the x values. So it's decreasing between negative 1 and 1. And again, open intervals. So just the parentheses there. Letter B. So increasing. Let's talk about increasing. There's one spot where it is increasing, and it's from here. So that is from negative infinity to 0. Then we notice it's constant in the next area here. So it's constant between 0 and 2. And then it is decreasing here. So that is from 2 to infinity. So see if you can try out these examples here for C and D. Pause the video, and when you come back, I'll have the answers. If you try this out, the first one, it looks like that it kind of stops here, but this is just all increasing. It's a cubic, so we're going to say it increases the entire way from negative infinity to infinity. Letter D, it's increasing here, so that's from negative infinity to negative 2, and then it's also increasing on this side, right? It's going up from left to right, and that is from 0 to infinity. It's decreasing in the center, so that is from negative 2 to 0. So remember that slope equals a rate of change. So for a nonlinear graph, the average rate of change is the slope of the line through 2 points on the graph. The line through the 2 points is called a secant line, denoted as m sub sec, like m sub secant. So average rate of change of f from x1 to x2 equals f of x of sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. So it's basically your change in y over the change in x. So Example 6, average rate of change of a function. Find the average rate of change from f of x equals x cubed minus 3x. So we do need to use that formula. So we know that f of x sub 2, so f of negative 1 minus f of negative 2 all over negative 1 minus a negative 2. So at f of negative 1, we know that our y value is 2, so it's 2 minus f of negative 2, which is also a negative 2, all over negative 1 plus 2. So this becomes a 4. Okay, so the slope of the secant is 4, and that's a positive slope. So let's try from x sub 1 equals 0 to x sub 2 equals 1. So we do the same thing. F of 1 minus f of 0 over 1 minus 0. And so at 1, that is negative 2. And at 0, so minus 0 over 1. So this is just a negative 2. So the slope of the secant line is going to be negative 2, and that is a negative slope. So you can go ahead and try this example here. Find the average rates of change of f of x equals x squared plus 2x. So if you tried it out for the first example, that would be a negative 3, and it's a negative slope. If you tried out the second one, that is 0 slope, right? If you look from these two lines here, that is 0 slope here. So the last example is finding even and odd functions. So a function is said to be even when its graph is symmetric with respect to the y-axis and odd when its graph is symmetric with respect to the origin. So here's a test for even and odd functions. So a function y equals f of x is even when for each x in the domain of f of negative x equals f of x. So when you plug in a negative for the x values, you get the original equation back. Then it's even. Now if you plug in negative x and you get negative f of x, so it's the opposite, the whole entire equation is opposite, then it is odd. Now if you plug in a negative x and it's neither, the perfect one you got back, nor is it the one where it's opposite, all opposite signs, then it is neither even or odd. So let's try this example, even and odd functions. To determine whether each function is even, odd, or neither, then describe the symmetry. So we're going to plug in negative for the x. So negative x cubed minus a negative x, we get negative x cubed plus x. So in this case, we get negative g of x. Notice that it's completely has opposite signs, so therefore it's negative g of x. So this is odd. Therefore, it is symmetric over the origin. Okay, let's try the next example. If we plug in h of negative x, we get negative x squared plus 1. So this just gets x squared plus 1. We get the same exact equation back. Therefore, this is even, and it's symmetric over the y-axis. So if you look below, symmetric to the origin, this is an odd function, this is the graph. And so you can see that it is symmetric over the origin right here. And then the parabola, this is symmetric to the y-axis. So if you'd like to get more practice, you can go ahead and try these next three, and you can pause the video and I'll have the answers when you come back. So if you try this out, you get 5 minus 3x, you plug in a negative for the x, it is neither even or odd. Letter B, if you try that out, if you have an even power, then you know that it's going to stay the same side, it's not going to change. So therefore, it stays the same, and it's even, and it's symmetric over the y-axis. And the last example, you have odd powers, so therefore they change signs. And then everything changed signs, so it's negative h of x. Therefore, it's odd and symmetric over the origin. I hope this helps. Thanks for watching.